Hello, my name is Bharat Biswal. I'm a distinguished professor in the Department of Biomedical Engineering here at NJIT since 2012, so about a little more than 12 years. My primary research interest is in biomedical imaging and studying brain function. I teach both graduate and undergraduate students medical imaging and biomedical signal processing. My primary research interest is looking at brain communication between different regions of the brain, primarily during resting state while the patients are not performing any task. When I started my PhD in the early 1990s, Medical College of Wisconsin was one of the few places in the world where one could study brain using functional MRI. In addition to collecting high-resolution images of the brain, one could collect every second or so an additional image. So instead of collecting a single brain image, one was basically collecting a movie. If you wanted to look at their brain function related to motor, you would ask them to tap their finger or wiggle their hand. If you wanted to study their vision, you showed them pictures. To study the auditory cortex, you would make them listen to different text or sounds. While this was a revolutionary way to study brain function, my interest was to look at the brain while it was at rest. And what I found was that even during rest, these functional regions like the sensory motor cortex, the visual cortex, or the auditory cortex, and many other functionally related regions had unique signal characteristics among themselves. So you could just look at a resting state signal from the sensory motor cortex and you could identify the sensory motor cortex without the subject having to perform the task. In a number of cases like stroke or traumatic brain injury, or infants or people who cannot follow instructions like Alzheimer's disease, it's not that easy to ask the subject to perform a task. My current grant, which has been funded by the National Institute of Health to study Alzheimer's fMRI data, is to look at gray matter signal changes and then look at white matter differences between Alzheimer's and matched healthy control. We have shown that there are significant differences between these white matter signal in Alzheimer's compared to healthy subject. So we are looking at trying to integrate both information from gray matter and white matter to improve the ability to differentiate healthy subject from Alzheimer's subjects. So the field is moving a lot towards using machine learning and deep learning methods for prediction accuracy. There's a quote by Edison that the best way to predict the future is to create the future. So in terms of fMRI, I believe maybe in 10 years or so, there will be a lot of data. But what would make fMRI particularly useful is to make individual level prediction. Surgery is an obvious example where one can use fMRI to study brain function in the presence of a tumor. Other regions like psychiatry or neurology, disorders involving stroke, dementia, depression, ADHD. In all these cases, clinicians are routinely using fMRI to better understand brain function. And even when there is treatment, they are using fMRI as a way to study before and after the treatment to see how well the treatment is progressing. I would like to thank the selection committee and the senior administration at NJIT for selecting me for this award. But I'm particularly thankful to all the undergraduate researchers who, in spite of their very busy schedules, still make time and put in time to do research and contribute very meaningful work. The graduate students, the postdocs, and other colleagues who helped me in this research.